let us kind of so like I told you, right? So we have to show that this is related to a symmetrically extended sequence of the actual sequence you started with. Okay, so what we will do is, so its relation to so the claim is that, right, it can be computed at the same speed at which you computed DFT. Separable, of course, it is also separable. So when you go to higher dimensions, again you don't get hit. All your computations wise, we are quite good. Okay, and on top of that, it has these other properties, right? So naturally, that makes it attractive. So relation to DFT, so which then means that if you can show that this is related to DFT, then it means computation wise you can in fact use a DFT to arrive at this. Okay, but for that we have to first of all establish what is that relation between that this has with respect to a DC with respect to DFT. Okay, so in order to establish that, right, we'll have to go through a small little sort of a proof. Okay, so let us construct sequence yn as follows. So you construct it as yn is equal to un. So let us so you started with the sequence un. Okay, so you're looking at DCT of u of n from 0 less than n minus 1. So it has a length n. Okay, and we want to show that this is somehow related to the DFT of this guy extended in some manner. Okay, so y of n, so we construct y of n to be equal to u of n for 0 less than or equal to n less than or equal to n minus 1. And then it will be u of 2n minus 1 minus n. So that's that symmetric extension for n greater than or equal to n and less than or equal to 2n minus 1. Okay, so you have sort of extended the sequence such that it has a length 2n now. Right. So now, if you compute DFT of yn, compute DFT of y of n, what will that be? Let's call this as yk. Right. What will that be? 1 by root 2n. Right, because you have 2n length. No, the sequence is length 2n. If it was n length, we would have written 1 by root n. It has length 2n now. So 1 by root 2n, summation going all the way from 0 to 2n minus 1, because yn has 2n length. So 1 minus 1, then yn e raised to minus j 2 pi by, I can't write n now, I have to write 2 pi by 2n. Whatever is this length here, e power minus j 2 pi by 2n kn, and k going from 0 to 2n minus 1. See, it might appear to you that initially on the face of it, it might look like, oh, then, right, does this mean that I have to take a kind of a 2n point DFT in order to, which may look like more work instead of n point DFT, but we will show eventually that you don't actually compute anywhere a 2n point DFT. Okay, this is only to start the exercise, and then along the way, right, we will show that actually it is not required to compute a 2n point DFT. Okay, so now if you look at it, right, suppose I have the sequence. Let's go back to that sequence. Okay, where you had 0, 1, 2, 3, 4, 2, 3, 4. Okay, this was your un, let's say, right, versus n. So what you have done is, so this is u0, u1, u2, u3, u4. Right, those are the values. So you are computing your yn now, you are plotting yn versus n. So from 0 to 0, 1, 2, 3, 4, it looks exactly like un. And at phi, right, if you look at it at phi, you have to come here to this below guy. So what is the length of this? It has a length n equal to phi, no? So it will be 10 minus 1, 9, minus 5, 4, right? So which means that this is like u4. Then 10 minus 1 is 9, minus then 6 is u3, right? So it will be like u3, so this is u3, right? And then u3, u2, u1, and then 6, 7, wait a minute, 8 and then 9, right? So at 9, okay, you would have hit U0. Okay, so computing a 2D DFT, right, of the sequence means right, that this guy will start to again, so this whole sequence will start to repeat, right? So it means that at 10, okay, you will have this, and then it will start to go up. So now you can, of course, and this will also repeat from the left. So you see that right, you have made sure that right, that this and your right, and that value, which is the beginning and the end value of y of n, right, they match, right, they're equal, and then that is one way to see that this false jump that you got otherwise, right, is gone. Okay, so un can be anything arbitrary, but then once you extend it in this manner, then it's clear that I get a yn sequence wherein I won't see this unnecessary jump happen. Okay. See, different people call it, in different ways. They call it spectral leakage for a DFT. Yeah, different people call it by different names. Now that we have this, okay, what we will do is we will now yk. Okay, now let's just split this as okay, 1 by root 2n summation n equals 0 to n minus 1, and for that, right, yn is un, right, e power minus j 2 pi by 2n, and in a hurry, right, we will not try to cancel this 2. Okay, don't be in a hurry to cancel it off, because you need that 2n when you look at that cos, no, in the bottom it has a 2n, right? So that is why we don't knock off this 2n. Okay, we keep it, we carry it along with us, plus then 1 by root 2n summation n, okay, whatever you want to call it, okay, let's call it m or n, it doesn't matter, we know that n is equal to z, n equal to n to 2n minus 1, correct, and in that range it is u of 2n minus 1 minus n e raised to minus j 2 pi by 2n kn. Right, so we have only split it into what we know, right, what yn is like over 0 to n minus 1, and what yn is like over n to 2n minus 1. Now if you focus on this expression, right, let us say let L be equal to, what is that, 2n minus 1 minus n. Okay, so when n is equal to, what is that, the lower limit is n, no, so L is n minus 1, correct, and when n is 2n minus 1, L is 0. Okay, so focusing on the second term, what do you get? So you see that turns out that can be written, it can be rewritten as written as 1 by root 2n summation any value equals 0 to n minus 1, right? I can write it as going from, because those are all the only terms that are involved. And then what do you have? U of L e raised to minus j 2 pi by 2n k, and then replace n by L, right? So that will be 2n minus 1 minus L. K still goes from 0 to 2n minus 1. This is okay, no? Or in other words, we can come back to that expression and say that yk is 1 by root 2n. Okay, 1 by root 2n, and then we can actually sum it up, because this sum is also going from 0 to n minus 1, that sum was also going from 0 to n minus 1. So simply write it as n equal to 0 to n minus 1, except that first case you had un e raised to minus j 2 pi by n kn, and now you have plus un e raised to minus j, what can we do, 2 pi by 2n, I know, wait a minute, k 2n minus 1 minus n, right. Now if you look at this one, e raised to minus j 2 pi by 2n k into 2n into e raised to j 2 pi by 2n into k e j 2 pi by 2n kn. 2 pi by 2n. Yeah. Okay. The x. Oh, you mean to say here, huh? Yeah. Thanks. I missed that. Yeah, that has 2 pi by 2n. Yeah, here, no? Here it is, 2 pi by 2n. Yeah, so now if you look at it, right, this 2n will cancel off, and ej minus 2 pi k for k integer is 1, right? So this just bows out, and then you are simply left with this term, and you are left with this term. Okay, so then this becomes 1 by root 2n summation n equals 0 to n minus 1 un e raised to minus j 2 pi by n 2 pi by 2n kn plus un e raised to j 2 pi by 2n k e raised to j 2 pi by 2n kn. Okay, now you play a small trick, all this is done because to bring it in that form. Okay, so what would you do? You would take out pi, what is that, pi k by say 2n out. Okay, take pi k by 2n. Okay, so yk, so e raised to okay, where is that, 1 by root 2n. So you take out ej pi k by 2n, take it out, then you have a sum going from n equals 0 to n minus 1, and then you have un e raised to minus j 2 pi by 2n kn, but now this guy never had any pi k by 2n term, therefore it will become e raised to minus j pi k by 2n, right, because it does not have anything like that. Next one will be un, and what did it have? It had ej 2 pi by 2n kn, so e raised to j 2 pi by 2n kn, and then the other term, right, is this one, which is ej 2 pi k by 2n, and you have already taken ej pi k by 2n out, so this becomes ej pi k by 2n, correct, because of this term. So this is 1 by root 2n e raised to j pi k by 2n summation n equals 0 to n minus 1 un e raised to minus j k 2n plus 1 see, so here it is into pi by 2n, correct, and I pulled out k is common, and I pulled out k pi I pulled out as common. So one case you will get 2n, and other case you will get 1, and minus j of course is common, right, plus un e raised to j. We should do the same thing here, k, this is k, okay, it looks like u, should be kn. ejk ejk 2n, because pi we will take out, so ejk and then pi on this side by 2n. So now, right, you start to see the similarity, no, until like e power minus j this one theta plus e j theta, right, un is common, so this is e raised to the form e raised to minus j theta plus e raised to j theta, right, theta is the same, minus theta plus theta. So therefore this will make it so you will get 2 cos theta, right. So the 2 let us knock off here, so you will get root 2 by n, okay, and then e raised to j pi k by 2n summation n equals 0 to n minus 1 un cos pi into 2n plus 1 k by 2n. K less than or equal to 2n minus 1 still. Okay, this is yk. So now you see that, right? I mean, see, when we kind of say derived yk, we simply took actually a DFT, right? We didn't take DCT at all. We took a DFT. But then eventually, okay, what we have ended up showing is that right, this expression sitting inside, this is of course, a DCT of u of n, right? You can see a DCT sitting there. So which actually means that right, if you right, if you're interested in Vk, right, which is actually which is this, right? This is what you're interested in. So what you can do is, if you want V0, right, let's say, because V0 will mean that this guy will drop out actually, because this will become 1, right? And then so what is that relation that we had? So 1 by root n, right? Alpha 0 was what? So you need, so your V0, right? This involved, the alpha 0 was 1 by root n, right? Whereas alpha k for other values was what is that? Root 2 by n. What is that? Root 2 by n or 1 by root 2 by n, I thought, right? What did I write there? Root 2 by n, right? So for other alpha. So now keeping that in mind, right? So if you look at it, so your alpha k, which is multiplying it from outside, right? So this expression had an alpha k, right? Extra. If you go back, right, here we had this alpha k sitting here, right? So this inner one is what you are seeing out there, right? This expression you are saying, and there's an alpha k, right? That also we have to account for. So the alpha k is such that for k equal to 0 is 1 by root n. So if you put k equal to 0, right, and if you want, so it's like saying that if I take y0, right? So y0, if I want to express it in terms of y0, but then y0 has this root 2 by n, correct? So if I want to knock this off, so I should simply multiply it by 1 by root 2, right? If I do 1 by root 2 times y0, then it will give me actually v0, because then it becomes like 1 by root n, e power j pi k is gone because k equal to 0, and then the other term is what we had there, correct? So for v0, this is what I can do if I want to derive from yk, and for other k, right, vk, there anyway I need a root 2 by n, that alpha k. Okay, so all that I have to do is cancel this guy off. So e raised to minus j pi k by 2n yk, right, will give me for 1 less than k less than or equal to n minus 1. Correct, because I need k for v I need only up to n minus 1, right? I don't need beyond that. That's all I need to compute my vk, right? So you see that so the explanation, right, that we had, why this can actually pack, right, more energy in the first few coefficients is because implicitly, right, computing a DCT, you can also implicitly visualize it as computing DFT of the symmetrically extended sequence. So if you are computing DCT of u of n, it is equivalent to extending it to a length of 2n, making it a symmetric sequence, and then computing a DFT of that. And because you know that computing a DFT in that form, right, does not involve jumps and so on, therefore you expect, right, those coefficients to die faster, right? So okay, one way to kind of, right, interpret the fact that DCT can pack more, right, is because of its inherent relation with respect to DFT. So based upon what happens when you compute a DFT, we can now go back and explain, right, as to why a DCT can be expected to do, right, can be expected to be superior, right, than actually a DFT. Although, right, there is also this relation with the DFT, but that is in fact what actually throws light on this. Now the only thing that really remains is, it looks like, right, I have to compute a 2n point DFT, but that is also not true, right? So this point is, the second point is easy, because you know that, right, computing yk, right, when you have yk going from what is this, 1 by root 2n, right, you had summation n equals 0 to say 2n minus 1 yn e raised to minus j 2 pi by 2n kn, right? When you have this, we know that we can split this into even and odd. So we can write this as 1 by root 2n and summation n equals 0 to n minus 1, let's say y of 2n. Okay, that will capture all the odd values. So sum I have changed it from 0 to n minus 1, right? E raised to minus j 2 pi by 2n k into 2n. right, because n should be replaced by 2n, no, right, plus 1 by root 2n, then you again let the summation go from 0 to n minus 1 to cover all the values. So y of 2n plus 1, all pick up all the odd values, e raised to minus j 2 pi by 2n k into say 2n plus 1. Okay. Now this is simply some y e of n, right? If you wish, you can call this as all the even values sitting in y. These are all the odd values sitting in y. So this, so right, so these two have length n, and now, right, you can cancel off this 2, right? So this 2 will knock off this 2 here, of course, and you'll get one extra term coming out, but then the point is, okay, let me write it down. So this is like 1 by root 2n summation n equals 0 to n minus 1 y e of n. Okay, this is length n, because the whole length is 2n minus 1, right? So this is length n, e raised to minus j 2 pi by n k n, because that's 2 and 2 got cancelled, plus 1 by root 2n summation n equals 0 to n minus 1 y odd of n. This is like the odd values, so this is again length n, and then e raised to minus j 2 pi by n k n into, so this other term, right, is what, into e raised to minus j 2 pi by 2n k. Okay, and anyway, this is independent of n, right? So therefore, right, this can be brought out. Okay, I mean this you know, right? This is a standard way in which you do sort of, you know, a decimation in time, right? So this can be brought out because, you know, it is not dependent on n, so it just comes out, and therefore, right, clearly you can simply, and computing this is equivalent to computing an n-point DFT. Right, computing this is again equivalent to computing an n-point DFT. 2 pi by n k n, lengths n, right? So it is equivalent to computing n-point DFT, and therefore, if you simply compute this and find out y just for the first n minus 1 values of for just for k running from 0 to n minus 1, you have your Vk, right? So what this shows is that so because, right, all operations can be done using a fast Fourier transform, in fact, right, even though to get right, begin with it wasn't so apparent, but because all this can be done using an FFT, therefore what do you call, the order, right, for this is n log n to the base 2, which you can compute at the same speed at which you would compute an FFT, right? So the computational complexity, right, if you talk about a DFT, DCT, computational complexity is in fact, right, it has real values, so that way it's even faster, but the order is like n log n to the base 2.